Good day, everyone, especially to the two of our professors here, Sir Jingle and Sir Dennis, and to our students. Good day to all of us. Today, I'm going to have a practice teach in Physics 103.1 Thermodynamics Laboratory. I am Jardy Delicana, and you can contact me if you have questions in the email that I provided below. Today, I'm going to talk about the mechanical equivalent of heat, the concept, and the experimental setup. Before the mid 19th century, never has it known that the mechanical energy has its equivalence to heat energy. And in in some systems, the final states are indistinguishable. That means that you cannot tell whether the gas reached the final state by being heated, having work done on it, or a, a combination. And so, as we can see in the leftmost image here, that a force is done in the system associated with the distance, and that is the work that is done on our gas in this case. And the final state, it has been observed that the temperature has raised to 200 degrees Celsius from the initial temperature of 100 degrees Celsius. And this is the same when we put a direct source of heat, for example, a burner, here to our system, and the resulting temperature is also 200 degrees Celsius. So there could be a very good relation, or they could be a very close relation to this energy. And this is now what we are talking about, the mechanical equivalent of heat J. This is the number per units of work divided by the unit of heat Q. And equation form J is equal to W over Q. J is constant and independent of magnitude of W and Q. And the standard units are 4.186 joule per kilocalorie. This is the small calorie here times the Kelvin, or 778 feet times pound divided by the BTU. This is the British thermal unit, and this are equivalent, only that it is scaled in different manner. And this is now, the J now is the amount of energy that is needed to raise the temperature of 1 gram of water to 1 Celsius degree. The amount of energy that you need is 4.186 joule to raise 1 gram of water to 1 Celsius degree. And you might ask why we use J here. This was in honor to James Prescott Joule, an English physicist, which was born on December 24, 1818, and died on October 11, 1889. And he was the first to demonstrate the mechanical equivalent of heat in 1843 in this type of experiment. And this has led us to the concept of the first law of thermodynamics, which is the conservation of energy, which states that energy can neither be created nor destroyed. It can only be transformed into another form. And then the assertion that is being concluded from this first law is that a constant ratio exists between mechanical energy and heat energy when either form is converted into the other. And this is the very reason why we can use power plants, refrigerations, and the very reason why we can harness the power of engines. And let's go to the experimental setups. This is the classic experiment of Joule. It has the thermometer here, mass or masses in here. This is now the ruler, or any device for measuring the height, the change in height of this mass here. And we have, in this experiment, in this case, he used water, and then the paddles here, the string, the hand crank, and the calorimeter container. This will help us measure the temperature, as it would not allow a drastic change in the temperature in our water. So the concept here is that the mechanical energy that is sourced from that is in the form of potential energy that is sourced from the change in the position of our mass here, that is triggered by our crank, is transformed into kinetic energy, and this would kinetic energy in the string, and this would be transferred into our paddles, and this would turn our paddles. And this in turn, this kinetic energy would be transferred into heat, and our thermometer would record this change in in the temperature. So you might ask how this has happened, that the potential energy is transformed into kinetic energy. Well, this is readily evident, and the kinetic energy is further transported into heat. And um, you might also wonder that if you turn the crank here for a single time, and then it would turn our paddle here, um, you will notice that this paddle would in some time would come to a stop. So you might wonder where is the kinetic energy would go, because according to the first law of thermodynamics, that energy can either be created or destroyed. So the kinetic energy is transferred to our water, and that the molecules of our water gain the, energy due to the bombardment of this paddle. And later you will know that the average kinetic energy is just our temperature, and our temperature is a measure of our heat, and so we can record that in our thermometer, and thus we can have our change in temperature. And in equation forms, if not, the mechanical energy in the form of potential energy is equated into heat, as we have shown in the experiment. And we know that the potential energy is equal to mgh, and this is the heat is in the quantity q. And we know that the q now is equal to um, the specific heat capacity, and multiplied by the mass of the medium. In this case, in our experiment, it's water. So I put here m sub H2O, and then delta T times delta T. So we can equate this uh, two terms here. mgh is equal to Cm sub H2O times delta T. And we can calculate the specific heat of our material here. And this is a constant, and this is unique in different type of material, and this in turn now is equivalent to our J here, which is equal to W over Q. So as you have noticed, they have the same unit. So if you solve these things here, you have joule per not times. This is divided by kcal times the the temperature change and temperature here. And this term here is being expressed as um, a unit of temperature, and then the degree is written after it. So this is treated as a Celsius degree, or for in case you use the Fahrenheit, this would be the Fahrenheit degree. This is different with degree Celsius, because this is now the actual temperature of the material. This is the change of the temperature of our material. So you have to remember these things. This is important in our calculations. And so in another setup, so we have I have to state here that this is the general form that we generated. And in the experiment of Joel, he discovered that you have to turn the crank multiple times in order for a net change in temperature here. So we have to multiply it with the number of repetitions and here. And you might ask where this two came from. This is from the two masses that is being used in this experiment. So the potential energy would double, and of course multiplied by the number of repetitions that we sourced our potential energy in this experiment. And yeah, I have to mention the drawbacks of these setups. This is only efficient for fluids, most specifically in liquids. Uh, for metals, this would be less efficient. And so we have another method, the shot tube method, and this comprised of a tube here. This is actually a PVC tube. Um, this is the one that you're supposed to be using in your experiment if you had a face to face. So what we have here is the metal shots is being placed in the inside our tube, and the empty space here in inside our tube is now the H. This is where our shot is being displaced by this change in height. And then to measure the change in temperature here, we have a plug here, and then you replace it with the thermometer. With the thermometer later on, if you will measure the change in temperature. And the formula that is expressed here is the work is equal to the acceleration due to gravity g times the mass of the metal shots times the height, in this case the empty space of the PVC tube, and then multiplied by n. This is the number of 180 rotations. This is just the change in your height, or the number of times you change your height. And what I mean with 180 rotation there is that in your actual experiment, you actually do it in a quick inversion, 180 inversion, and then back to its original. So you have to do it quick before the temperature uh, would would return to its original state again. So I think that's it for um, the concept and the setup. So I have learned something today. Thank you, everyone. Mega Basasol, and these are the sources of my report. And thank you once again, and keep safe, everyone.